Hello, my name is Derli. We'll start my presentation. Let me share my screen here. Um, yes. So my name is Derli Amaral. I will talk about numerical thermohydraulic comparison of shaped in radial flow networks for cooling uniformly heated disks. My professor here at SMU, José Lage, is the co-author for this paper. Thank you so much for having the opportunity to participate in this very good conference again. It's my third time. Let's go start. So my work is based on constructal theory. So if you pay attention in nature, we have similar designs. For example, river bases, our lungs, and trees. So we can ask ourselves how nature developed this such a design. And the answer for constructive theory is that there was evolution, there was design in nature that allowed the nature to have such of a similar pattern. So you can use that to make components. For example, this fin here is used in a more efficient way to remove heat out of a heat generating volume. So the constructive theory, it's about not mimicking nature, but predicting nature when the evolution in time is the target. Okay, so based on that, we studied four geometries that it's listed here. Two of them is with n equal to 6 outlets, and two of them are equal to 12 outlets. And the idea is to compare the radial flow against the complex flow, or bifurcated flow, or tree-shaped network flow for n equal to 6 and 12. And the idea is primarily is to see what is the best geometry in terms of hydraulic resistance and thermal resistance. So which means that what is the best geometry that would yield lower pressure loss and would yield the lower maximum temperature. So here we have a zoom in of our geometry that was made using 3D solid works, and then we have the flow here entering the geometry and leaving at the periphery. So here the diameter of this patterns follow the Moore law. It means that we have a higher diameter at close to the origin compared to the periphery of the disk. So it follows this law here, which is the Moore law, which is the famous law from biology. Okay, so here from all these four geometries, we have the geometries parameters, the disk radius, the diameters of each of the geometries here. So for this geometry here, we have the fluid and the solid. So one idea here was to compare this four geometry in terms of K star, which means that we're gonna change the solid divided by the fluid thermoconductivity and producing 1, 4, 12, or 18, 63, and 267 K star, which means that when you have 267, we have a very distant thermoconductivity from the solid compared to the fluid. And the range of Reynolds number is from 0 to 2000. So one can derive this equation here. It means that for the radial, the Reynolds of the radial geometries is very close to the Reynolds of the periphery of the bifurcated geometries. Okay, so here we have the governing equation of Navier-Stokes, and that we use it, an energy equation, and the boundary condition and the assumptions that we use it here. So basically more important here that the fluid, the velocity is poop developed at the inlet, and then the temperature of the fluid at the inlet here is 0 Celsius degree, and the pressure is ambient pressure at the exit, and the rest is um, insulated. Okay, so according to the previous work given by Vegetal et al., it says that the radial networks with no bifurcation yields the best thermal performance, which means that produces the lowest thermal conductivity. And the more complex flow with the tree-shaped networks would yield lower delta P or lower F, which means that would produce lower pressure loss. So this F here is the dimensionless fluid resistance. So we have here our 4 geometry based on that. So for n equal 12, the radial geometry should present a higher delta P compared to the n equal 12 with 2 bifurcations. So we start the results. So this is the delta T. Delta T is the maximum temperature. It occurs here, the periphery of the disk, minus the T naught. So the lower the delta T, the better. So the configuration that produces the best performance in terms of thermal resistance would be the one with K star equal to 260 compared to the others here for n equals 6 for bifurcated flow and radial. So the same behavior happens when we have n equal 12 with 12 exit, 12 outlets. So we have the K star equal 260 presenting the lower maximum temperature is even more evident when we go very close to the limit of our flow range here, or the limit of the laminar flow. So here is the graph for the K star equal to 1. So we compare the 4 geometries. And then, for example, for Reynolds equal to 6, very close to the beginning of our flow range. So we can see how the temperature here goes down as we change the flow, the configuration of the geometries here, right? So the best geometry for K star equal to 1 would be radial with 12 outlets. Here we have the T star. The T star is just explaining you the same as delta T, but it's dimensionless. So for K star equal to 260, here we just presenting the K star equal to 260 that shows the best performance against all other K stars. So for that, our geometry with 12 outlets bifurcated presented the best performance in terms of thermal resistance. So now we can go to the Nusselt number. The Nusselt number is a way that we can assess how the geometries is exchanging temperature between the fluid and the solid. So the best geometries are those with bifurcated flow here. And it's more evident again when you go to the limit of our flow range. So this is the results for Nusselt number. And then here we have some examples of how we did the numerical simulation. Here we have the velocity at inlet, fluid temperature, pressure loss, and here we have the flow very close to the bifurcation. It means that we have here some circulations on the bifurcated flow. It yields more pressure loss. So talking about pressure loss, so if we plot the delta P over the Reynolds number, we can see that the best geometry here is n equals 6, the radial flow for the entire range. So this is against of what was expected. So we can plot we can talk about fluid resistance in plotting the graph with F, with the dimensions dimensionless fluid, resistance against the mass flow, and then this graph here, according to the theory, should be constant all the time. But you can see here for bifurcated flow, we can see that this number here started changing, going up after Helmholtz around 300 for both of the setup rate, n equal to 6 and n equal to 12. And this is not expected as well. So our conclusion here, we can say in summary that decision to choose the flow network with the best performance in terms of thermal resistance and flow resistance depends on factors that go beyond the network being radial or bifurcated. So for example, for thermal resistance, we have the best geometry, the radial with 12 outlets is the best one if you consider K star equal to 1. So when K star equal to 260, you have the best geometry is the bifurcated one with 12 outlets. For flow resistance, we depend on the Reynolds number. So the Reynolds number here for lower than 300, we have bifurcated geometry, the better, and for 300 to 2000 is the radial flow. So this work here brings more understanding and more analysis and conclusions that expand our knowledge for constructal theory in terms of convection. Thank you so much. Bye-bye.